Somewhere inside your car's engine, there's a tiny piece of metal creating sparks, around 1,500 times every minute. Each spark happens under extreme heat, hot enough to destroy most materials, and yet this metal keeps going for years without breaking down. That same metal helped scientists solve one of history's biggest mysteries: what happened to the dinosaurs? It's also used in cancer treatment, placed inside the human body to fight disease. And for many years, it even played a role in defining the standard kilogram for the entire world. Most people have never even heard of it. It's called iridium, and despite being one of the least talked about elements, it might be one of the most remarkable on the periodic table. Iridium is a precious silver-white metal, hard, brittle, and one of the densest substances found naturally on Earth. It's so dense that a small piece feels surprisingly heavy in your hand. It belongs to the platinum group metals, a family of elements that are among the rarest mineral resources in Earth's crust. Most of the world's known iridium comes from just 3 major geological regions: the Bushveld Complex in South Africa, the Great Dyke in Zimbabwe, and the Norilsk-Talnakh intrusions in Russia. Its name comes from the Latin word iris, meaning rainbow. When English chemist Smithson Tennant discovered iridium in 1803, he was studying crude platinum. He dissolved it in aqua regia, a powerful mixture of nitric and hydrochloric acid, and examined the black residue left behind. After treating it with different alkalis and acids, he realized it contained 2 entirely new elements. He later announced the discovery at the Royal Institution in London. For that work, Tennant received the Copley Medal from the Royal Society, its highest honor. Of all the metals on the periodic table, iridium is the most resistant to corrosion, even at temperatures reaching 2,000 degrees Celsius. In its solid form, it is almost completely unaffected by acids. It won't dissolve, and it isn't attacked even by aqua regia, the same acid mixture famous for being able to dissolve gold. It's also the only metal that can keep strong mechanical properties in air at temperatures above 1,600 degrees Celsius. By that point, most metals have already weakened, warped, or completely failed. But iridium does have one major drawback: it's incredibly difficult to work with. Pure iridium is so hard and brittle that machining it, shaping it, or welding it in solid form becomes a serious challenge. That's why it has relatively few direct applications on its own. Instead, industries usually work around this by using powder metallurgy or by mixing it with platinum. Even a small amount of iridium added to platinum can dramatically improve the strength, durability, and heat resistance of the final material, which is exactly why iridium ends up in places where failure carries consequences. In your engine, for example. Iridium alloys are used in spark plugs because they resist arc erosion far better than cheaper metals. A spark plug has to fire again and again under intense heat, pressure, and chemical stress. Most materials wear down quickly. Iridium lasts for years, which is why it became especially important in high-performance and aviation engines. In your screen, iridium helps create light itself. Iridium-based compounds are key parts of white OLED technology, the light-emitting system used in many modern phones and televisions. These compounds are incredibly efficient at producing bright, accurate color without wasting large amounts of energy as heat. In cancer treatment, a radioactive isotope called iridium-192 plays a major role in brachytherapy. This is a treatment where the radiation source is placed directly inside or beside a tumor, allowing doctors to target cancer with far greater precision. According to the International Atomic Energy Agency, high-dose rate brachytherapy using tiny iridium-192 sources can deliver more than 12 grays of radiation per hour, making outpatient treatment possible. Stanford Healthcare also notes that because iridium-192 is so energetic, doctors can deliver the needed dose in just minutes, without exposing the patient's family or hospital staff to radiation. And in measurement, iridium once helped define mass itself. The International Prototype Kilogram, the official standard for the kilogram for more than a century, was made from an alloy of 90% platinum and 10% iridium. For generations, every scale in every laboratory on Earth was ultimately traced back to a single platinum-iridium cylinder stored in a vault near Paris. That standard remained in place until 2019, when the kilogram was finally redefined, using a fundamental physical constant instead of a physical object. And then came the discovery that turned iridium from a rare industrial metal into the center of one of science's biggest debates. In 1977, geologist Walter Alvarez was collecting rock samples near Gubbio in Italy when he noticed something unusual: a thin layer of clay sitting exactly at the geological boundary between the Cretaceous and Paleogene periods. That boundary marked one of the most dramatic moments in Earth's history: the sudden disappearance of the dinosaurs. Walter sent samples to his father, Luis Alvarez, a Nobel Prize-winning physicist, who passed them to nuclear chemists at Berkeley lab for analysis. What they found was astonishing. That thin clay layer contained about 600 times more iridium than the surrounding limestone. That shouldn't have been possible. Iridium is extremely rare in Earth's crust, but it is far more common in meteorites. A team led by Luis Alvarez, Walter Alvarez, along with Frank Asaro and Helen Michel, proposed a radical idea. A massive asteroid or comet had struck Earth, spreading iridium-rich debris across the planet and triggering the mass extinction event that ended the age of dinosaurs. They published the idea in the journal Science in 1980. Why iridium specifically? Because iridium is what scientists call a siderophile element, literally iron-loving. When the young Earth was still molten, most of its iridium sank deep into the core along with iron. Very little was left near the surface. So when scientists found iridium spread across that global boundary layer, the conclusion was hard to ignore. It had come from somewhere else. Not from Earth, but from space.